Okay, so we just have a couple last ideas to wrap up from this section. The big idea, of course, is being able to determine when vectors are linearly independent, and then, of course, understanding what exactly that means. Now, uh, sometimes they'll talk about the columns of a matrix being linearly independent. Um, and so we have this rule. It's really nothing more than just the same rule, the same definition, but written with the from a matrix point of view rather than a vector point of view. So the columns of a matrix A are linearly independent if and only if um, AX equals 0. So there's our tradition, our regular homogeneous matrix equation. So if and only if the equation AX equals 0 has only the trivial solution. And of course, that's easy to translate that definition into the same definition that we had before that involved the vector equation. So it's not like we're doing anything different here. But remember, we've talked about this homogeneous system like this. When does it have only the trivial solution? It will only have the trivial solution when the matrix A itself, well, when there are no free variables in the matrix in the reduced version of matrix A. If there are free variables, then we have dependence. So that's one little thing to keep in mind. We already mentioned that when we think about a set of one vector, as long as that vector, so a single vector is always linearly independent. I guess we ought to say it this way. A single non-zero vector, as a set is always considered to be linearly independent. If it's 0, then it's easy to see that there are many solutions to a constant times the vector equals 0. But if it's non-zero, if it's a single vector, then it's always linearly independent. Now, if we take two vectors, just two vectors, and the thing about this is, remember, this doesn't matter if these vectors are in 2 space, have 2 entries, right, or 2 by 1, or in 3 space, 3 by 1, or 4 space. Doesn't matter, just two vectors. The rule is pretty simple. If the vector, if one, let's write it this way. If one vector is a multiple of the other, then they are then the vectors are linearly dependent. So if one is a multiple of the other, then the vectors are linearly dependent. There's a non-zero, non-trivial solution to the equation. You can build one vector as a product of the other. Anyway, so for two vectors, it's very simple. You just look at them and see, can I get one from the other by multiplying or dividing by a certain constant? So that's fairly easy there. And then finally, as we said, with I guess this is the case for vectors in Rn. Okay, so let's pick a space, say R3. For vectors in R3, the maximum number of vectors that can be linearly independent the maximum number is n. So in R3, right? So just this, I'll write this down. So in R3, of course, we can have at most 3 linearly independent vectors, right? And remember what these vectors look like in R3? They're 3 by 1s. So this is probably a set of 3 linearly independent vectors. But if I add any other vector to this, right? So we're in R3. If I add any vector, it does not matter. I don't even have to put any thought into this. That set is automatically not is dependent. Okay, because we're in R3 and we have 4 vectors. So just remember that. That's one thing to remember about linear independence. Okay, let's insert a little space down here. So now, what we just said does not apply to if there are, if there are fewer than n vectors in space. So, so if we're in R3, you can have 2 independent vectors in R3, but you can't have 4. And lastly, if any of your vectors, or if your set of vectors includes the 0 vector, then as a set, the set is dependent. If any of the vectors is the 0 vector, then the set is dependent.